So here's an example of this mechanism. And I think that this relates to homework number 3 as a mechanism problem with an amide. So we protonate the carbonyl group. That's job number 1 of the acid. Now our nucleophile water can attack the carbon atom. And we break the pi bond. We have this intermediate with the protonated alcohol group. This needs to be deprotonated. That's intermediate number 1. Job 2 of the acid is to protonate the amine group. And why is the amine going to be protonated over the alcohol? Because the amine has a stronger affinity, has a stronger pair of electrons. It's a stronger base. So that's more likely to pick up a proton than the oxygen. So this amine bonds to the acid proton. Now we have a protonated amine group. This is now a good leaving group. We can reform the pi bond and kick it off. This nitrogen group then will deprotonate the carbonyl group. We'll have ammonium and carboxylic acid as our products. And the reason that we need this catalyst is to make that nitrogen a better leaving group. Make it a weaker base. And better leaving group. Just like we did when we protonated the OCH3. I actually meant to delete this slide, but I guess I'll talk about it a little bit. The penicillin reaction is the conversion of an amide to an ester. And so the bacterial cell wall has this glycol coating, CH2OH groups on a glycol. This alcohol group will bond to the carbonyl group of the penicillin amide, and this amide bond will be broken. We go from having an amide to having an ester linkage, and that makes the enzyme in the bacteria inactive, and you end up getting holes in the wall, in the cell wall of the bacteria. There are many different penicillins. The variation is in the R group, and so let's just highlight the R group. Here's your R group. And so this is the difference that we're seeing here, is that R group can be replaced by any one of these molecules or appendages, and that will result in a different name for the penicillin. Amide hydrolysis can be promoted by hydroxide ion, and that is formation of the carboxylate salt that results from that. So we're replacing NH2 with OH minus, and then that OH is going to be deprotonated because we're under basic conditions. We can't protonate this to can't be protonated in base. Why is it still on highlighter? Pen. Okay, so we cannot form in base, not in base. That proton cannot be present if we're under basic conditions. So here is the mechanism for this reaction. We have hydroxide ion attack, break the pi bond, hydroxide ion deprotonates. We have our oxyanion intermediate, pi bond reforms, amine group gets kicked off. We have carboxylate ion, amide, and water. This amide is protonated to NH3, and we have our final product. We can exploit amides to form primary amines, and this is a very important reaction called the Gabriel synthesis. There's a question about it in item 12 of the homework. This is the changing of an alkyl halide to a primary amine, exploiting amide groups. So we start out with phthalimide, and phthalimide has this diamide. So we have one amide bond here, we have a second amide bond here. In base, we will deprotonate the nitrogen. Now we have a good nucleophile in this nitrogen between the two carbonyl groups. This N will bond to an R group that is bonded to an halide and kick off the halide in an SN2 reaction. Then we have a substituted imide, an N-substituted amide. So we have an R group on our nitrogen instead of a hydrogen now. And what happens when you treat an amide under acid catalyzed conditions, HCl and H2O? Let's go back. Under acid and H2O, what happens to this amide? We form a carboxylic acid and a primary amine. And that's exactly what's going to happen here. We're going to form two carboxylic acid groups, breaking these amide bonds. We form phthalic acid and a primary amine. Because we're in base, this amine becomes deprotonated, or the ammonium ion is deprotonated to the amine, and so are the carboxylic acids. So this is an acid-base reaction. An acid hydrolysis to form a primary amine. Other mechanisms to form primary amines include reduction reactions, oxidation reduction reactions. And so an acid-base reaction to form a primary amine is going to be more specific than other types of mechanisms. So one of the other mechanisms is an azide ion can form a primary amine through a reduction reaction. If we just use ammonia, NH3+, trying to form a primary amine, you're actually going to form primary, secondary, and tertiary amines. Reactions of nitriles. Nitriles can be converted into carboxylic acids under acid catalyst conditions because acid catalyst conditions break carbon-nitrogen bonds. And so what's going to happen is you'll cleave this and you're going to have C double bond O, OH, if you use HCl and H2O. Naming of nitriles, you're just going to have the total carbon number followed by the word nitrile, and it's all going to be one word, no space. We have ethane nitrile, benzene carbon nitrile, 5-methane, 5-methylhexane nitrile, and etc.